Yeah, hi everyone. It's a really nice gathering here and really happy to be here to give something that hopefully ends up being a concise overview of a number of different topics I've had the pleasure of working on over the years. And as Peter said, I mean, I've been at DeepMind for, I guess, close to 9 years now, so I've been there in the very early days and had the privilege of seeing some very early advances in AI when it was not as much of a hype topic as it is right now. But especially with the capabilities increasing rapidly, it really being integrated everywhere, I felt that for this talk it would really be appropriate to have a bit of a reflection on what can we do with these technologies we're developing at the moment. So I guess over the course of the summer school and looking at the program, there are many very exciting technical talks. And the way we ourselves sometimes like to think about the work that we do and the projects that we do is that we consider the what, the why, and the how of what we're doing. So we try to identify problems to solve, figure out why we are prioritizing, why we care about those particular problems in a space of many problems we could be working on, and then obviously the methodology that we employ, where there is a lot to talk about, obviously. So in terms of the contents of this talk, it's going to review a number of different projects, but it's going to focus on the what and the why in some sense, as well as when it comes to the how, not so much the how of the technical how, as in which type of model we're training or how we're training it exactly, but how do we set these projects up and how do we engage with the wider society in a way which leads to hopefully most positive impact. When it comes to the field of AI, you know, lots of us really who are in love with mathematics, and it's a very mathematical field, as well as are just genuinely curious, we're motivated and entered the field of AI and machine learning, just thinking about what intelligence is and how we can model something resembling, loosely speaking, the human brain, not to anthropomorphize the technology we're building. But at the same time, this allows us to solve many very important real-world problems. So that's the other side of the coin. And when I first joined, I guess the mantra of DeepMind at the time was something like, if you went to the web page, I don't think it's there now, but it said something like, solve intelligence and then use that to solve everything else. So in the spirit of that, this talk is pretty much about everything else. And in terms of the structure, I will try to give a little bit of an intro on AI for Good. I will review a couple of applications that I think are relevant, hopefully get some time to review some of our approaches to responsible innovation and challenges within the domain, and wrap up with a bit of a human-centered AI. You can ignore the fifth point. I guess the way we're going to do this, it would be ideal if we kind of aggregate the questions a little bit between these four sections. So I think that would be like a natural point to discuss some of these issues further rather than having like one long Q&A at the end. I've also been maybe a bit too ambitious in terms of how much there is in the talk, so I'll try to move very fast through some parts, be more reflective on the others, and if I need to skip something, I mean, hopefully the slides will be shared afterwards, so it should be fine. So in terms of AI for good, I guess one of the first questions we should ask ourselves is, you know, is AI good, just generally speaking? Because if the answer is a resound yes, then this talk is a little bit pointless because anything we do in this space is simply good by default. And in some sense, philosophically, and I'm by no means a philosopher, but a lot of people have been convinced, especially in the West over the long historical period, that progress is just genuinely good. And if we facilitate scientific progress, and AI is a part of scientific progress, obviously it allows us to do many great things, therefore that is in and of itself good. And that's a kind of a viewpoint that dissociates science from ethics a little bit, which just means we should just focus on scientific problems, solve them, and good will simply come out of it. However, knowing history, knowing human nature, this hasn't always been the case. And I think there is a very interesting intersection between the fields of science and ethics, which is not to say that progress is not good, but that amongst a large landscape of what we can do in terms of progress, we can still use some of the ethical guidelines to pick and choose what we do and how we do it, and that can inform downstream impact on society. So in terms of the term of good in general, whether you feel AI has been good on balance or bad on balance, I think most of us here are AI optimists. It's kind of interesting that it's a word we use all the time. yet very few people agree on what is meant by good. So when we say AI for good, it's sort of still important to stop and think for a little bit what it is that we mean by that. And I think many people here in the audience or many people amongst us may have some commonalities in our mental images of good, but there may similarly be differences. And while we're here in the Eastern European Machine Learning Summer School, so speaking geographically, a lot of us come from a similar part of the world, also cross-culturally and so on. There tend to be like more major differences in worldviews and what is perceived as good. So here are some definitions, loosely speaking. This is not meant to be comprehensive, but just to give an idea what we normally mean when we say common good or social good. That we develop technologies and solutions, products, software, or hardware, or non-technological artifacts at the end of the day, that are beneficial to all or most, and it is a distinction, right? Members of a community, because if it's not everyone, you have to ask who benefits, who doesn't. Improve the well-being of individuals, obviously as a consequence. How it's achieved, again, sometimes it's meant to be achieved more democratically, right, through community participation. A lot of people like to emphasize it not making inequalities worse. There are many inequalities of society. Some people mean specifically empowering groups that lack power in society at the moment. And there is this friction, it's not always a friction, but it tends to be a friction between working on short-term versus long-term. Even in things that we do, are we using the technology available now to solve something immediately? Or are we working on more hard, kind of open-ended scientific problems that, if solved, will open many things up? And finally, we want outcomes that align with some set of norms and values we have. So as AI started being stronger and stronger, all of these happened in the last couple of years. Obviously, a lot of policymakers started meeting in a lot of locations, which results in a lot of declarations. This is what policymakers like to do. Obviously, these should inform to an extent what we do as well. So I'm not going to review all of these declarations, but it's still worth just speaking into what is written there when it comes to the positive impact of AI in particular, and what are sort of the highlighted keywords here, what people like to bring up in terms of topics, applications, domain, where practically speaking, people see an opportunity for positive impact, like health, which will be a part of the talk later on as well, tends to be brought up kind of frequently. There is a lot of world hunger and poverty, so talking about human rights, food security as well, comes forward. Climate change, as we know, is a big problem, so clean energy and working on mitigating pollution and helping with the loss of biodiversity that it tends to come about, as well as clean energy. And something that's going to be a recurring topic here on these two slides, just the last point, is that the advances we make should be aligned with the UN Sustainable Development Goals. Now, I don't know how many people in this room, I would imagine most, but maybe not everyone, are kind of familiar with this framework, but it's another potentially useful framework of thinking on application domains. And each of these presented by the UN come with a set of priorities, metrics as well, and objectives that ought to be reached in a certain unit of time. And currently, we're not really meeting the pace of progress on all of them, but working on AI applications across these domains tends to constitute progress towards some agreed upon definition of common good. Finally, and this is also going to be a part of the talk later on, there is a very particular opportunity, maybe going back to what I was saying earlier, of seeing scientific discovery in and of itself as a vehicle for good. So a lot of work on AI for science will translate on AI for good, but it's not necessarily one-to-one mapping. And we'll discuss this a little bit more later on. One thing that's worth already maybe pointing out at this point is that we here are an assembly of, I guess, largely technologists, people from the backgrounds of mathematics, computer science, physics, engineering, and so on. And we therefore approach these types of problems as highlighted here from a technical point of view. So we try to build technological solutions to address some of the sub-points, obviously scoped far more modestly on lists like these. However, oftentimes that doesn't end up delivering the good that we want to deliver, and that's maybe the point of I'm trying to give this talk. So unsurprisingly, people notice this, and this is a reasonably old paper as well, where it sort of says that wanting to do good isn't good enough. And that shouldn't really come as a surprise. There are certain ways of engaging with these topics, certain ways of approaching them that are more or less likely to work. And what is one common pitfall is trying to map everything onto technology and ignoring the context in which it's applied, how it's applied, where it's inserted, working with other types of groups that can offer valuable insights, whether those groups are scientists, medical professionals, the rest of society. It very much depends on the use case in question, but it sort of speaks to the fact that because we are so competent in maths and computer science and machine learning and so on, we often, maybe it's ego, but we think that we can understand these other complex problems well enough to engage with them as well. And that tends not to be the case unless we actually engage with domain experts in those fields in a particular type of way. So one exercise we've done a couple of years ago was this seminar that was held at Dagstuhl at the time, which is in Germany, I guess, and it's a location that tends to host various types of slightly maybe offbeat, to put it that way, technical workshops, where we brought together, and this was organized by Tom and Claudia mostly, we brought together a set of machine learning people and a set of people who are driving changes in non-government organizations across Europe and beyond, to have a conversation. Now, many such conversations may have happened at the time. This was one of the very first ones, where we tried to figure out, okay, we have all of this technology, and you people have problems. I mean, the NGO sector is trying to address lots of gaps that have been unaddressed. Why is this not translating in between? And I'm not going to bother you with everything that we talked about, but I would like to highlight some particular things here in our set of recommendations at the time, which is that what at least back then was lacking, I think still oftentimes is lacking, is this notion of deep long-term partnerships. Now, if we, and obviously I don't know everyone's background here, think about how we oftentimes approach things, and there have been many examples of that, is that we come together and have hackathons or workshops or something of the sort. So whether this hackathon is 48 hours, whether it's a week, like however we set it up, we can, because we're technically capable, and there is some open data out there, and there are templates, and there are off-the-shelf models, we can quickly hack together some prototype. So we have an idea, and we just make something work plausibly. We may even spend another 1, 2, 3 weeks making it work more than plausibly, making it work well. But it still isn't enough, because there is no one on the other side. First of all, where is this other side? Which particular organization is deploying that in practice? They oftentimes don't have people with enough technical expertise to maintain that, deploy that, and use it in practice, track metrics, adjust. And for us, it's oftentimes a one-off. We've built this demo, we've handed it over, and we go back to our work because we had this volunteering opportunity, and we spent these 2 weeks working on that. But those types of engagements tend really not to work. And we may feel good about ourselves for having done it. We may tweet about it, post on LinkedIn, but it's not something that actually leads to solutions in the space. So to make these things work, we need to commit to something more longer term, and we need to build partnerships with people who are experts. And that takes time and takes energy. It's much slower, which is why people tend not to do it, right? So there's this phrase which is related today to that, which is launching is easy, landing is hard. And in the space of AI for good, we need to be thinking more about landing, less about launching, perhaps. Phrase-wise, I mean, there is even a phrase that relates to what I was talking about before, which is called tech, obviously intentionally misspelled, voluntourism, because we're tourists. We work in tech, and then we go on vacation to AI for good for a week or two, which again is not how we should be thinking about that, like ideally. Talking about recent examples, or maybe not so recent, depending on how recent it is in everyone's minds. But when the COVID-19 pandemic hit, there was this wave of interest in the tech community aimed at building solutions that would somehow help address the consequences of COVID-19, whether those were diagnostic tools or predictions of the spread of the virus, or one of the many applications area at the time. Yet that just ended up being pure noise. I mean, I remember being, on Twitter at the time, obviously being stuck at home like most people, and just seeing people from the machine learning community posting all of these preprints on archive, research papers, claiming to do something about COVID-19. And me having focused on AI for medicine at the time, I could see easily that a lot of them were simply done scientifically incorrectly. Unsurprisingly, it didn't go anywhere. It was even worse than not going anywhere because people who couldn't really judge the technical execution of some of these were spending energy and time trying to review them, and then energy and time trying to incorporate them. And that energy and time could have actually been spent on something productive at the time. So the incentives just weren't fully aligned, and the ways of engaging weren't good. And there were meta reviews doing afterwards, just finding that these papers, many of which were published in, at the time, even somewhat reputable venues that got lots of citations, just didn't amount to anything, with obviously a lot of criticism on social media that was later on unsurprising and so on. So yeah, not to maybe go into the details of that, but it's one recent lesson that even if we have the best intentions, and obviously when there is a worldwide pandemic, choosing to work on ML models that somehow map onto the pandemic seems like the good thing to do, wasn't actually the good thing to do. Speaking of similar phrases and maybe angles, there are these concepts of both techno-solutionism and also, I guess, the digital savior complex, which really comes from a perspective of all of us thinking we are so smart, and there are all of these technological solutions that can solve all of these problems beautifully. Sometimes that is the case, and we do what we do because sometimes that is the case, but it's not really generally a thing. And we should all be more humble, more modest, and talk to other scientists and people from other parts of society to facilitate the work that we do. So we should build AI, for sure. We should build it responsibly and aim to benefit humanity. And how do we do that? So I'll just stop briefly here, as I said, in terms of the structure of the talk, in case there are any early questions, and then we'll go a little bit into some of the application directions. Yeah, no? Okay. Well, you can interrupt me later on as well, so I guess that's fine. There are many things we could do. So looking a little bit more positively on the space of AI, you see these applications being shared, helping with disaster response. There is this, there are actually a number of very cool groups currently working on translation between human and ML languages. Apparently whales have a very rich communication sort of vocabulary and so on. We can use AI in education. We can use it to track species and ML behavior to help with biodiversity. We can facilitate clean energy. And we need this. So again, why are we really thinking about this rather than just hoping that there's going to be some downstream consequence of all of the commercial maybe action that we're facilitating through the models that we're building? We really aren't in a very good spot, right? So there is a lot of pollution that's impacting human health. We've lost most of the wildlife that existed. And climate change is reaching an irreversible point, right? And over 1 billion people still live in poverty. A lot of people don't have access to clean water and education and food and so on. So these are all very, very big, serious questions. And we have an opportunity, and we also have a moral responsibility of working on them. So if we can, obviously not talking about purely methodological work, but oftentimes we engage with real data sets, real metrics, real problems, we should really pick them carefully so that they contribute towards this. When it comes to sustainable development goals, as the UN has defined them, you can see in this first point that while there is this international commitment and the recognition of them being important, 80% of them aren't really on track. And some have even regressed. And that's, again, given their importance, not a good place to be. Most of these disproportionately impact the not so well-off and not so developed part of the world. And also there are some recent reports that are trying to map some of these stalled, unaddressed opportunities onto new emerging AI technologies, which I would encourage people to read, because while it's not a comprehensive report and it's a little bit kind of forward-looking, it may also help inform some of the topics we choose to work on. So this is how it looks as a kind of a breakdown. There's some green, there's some red. It looks a bit symmetrical, and that's not a good look because symmetrical sort of means like nothing is really changing on average, I would guess, right? Okay, these are maybe not human readable on the 17 listed, but you can see that some have regressed quite a bit, some have made some progress, and overall it sort of depends, and again, it's not a good place to be. So from that report, or those reports, you can see that like 2.5 billion people have food insecurity. More than half of the world is not really getting the health services that they need, so it's not a small percentage. And again, why medical AI may come later on in the talk as a big topic, and similarly challenges in education and so on. So one of the things we can do, and that we should definitely consider doing, is helping advance science. While not all science may necessarily gracefully map onto these positive applications immediately, scientific progress is one way, and when I say scientific progress, I don't mean machine learning scientific progress, but progress in sciences in general, is one way of unlocking technologies that may help with some of these problems. These problems are not, as mentioned maybe before, purely technological problems. They're social-technical problems. They involve the rest of the society and all of the application domains as well. But technology can, and I would guess will, play a role in the resolution in all of them. And it's up to us to make those advances to facilitate positive change. So in this part of the talk, I will review a little bit the potential of AI to be used for advancements in science, and how we see this as being one potential vehicle for making these types of changes. So DeepMind has been around for a while. There are lots of teams, lots of people that have done lots of projects. Obviously, these here I've not been involved with, but you've probably all heard about AlphaFold and its applications, advances in trying to make fusion energy possible, weather forecasting that help us address some of the consequences of climate change by issuing early alerts and warnings of adverse weather events and so on. So there is a lot that both we as a company are doing, but that the machine learning community at large is doing. And when we talk about science, one metaphor, I guess, that people often use is this tree of knowledge, or rather visualizing applications mapped onto something like a tree-like structure, where at the root nodes there are fundamental scientific advances that don't immediately have some kind of a social application. Those are a lot of advances in physics and mathematics and so on. And then there are areas closer to the leaves of the tree, obviously structured in some kind of a hierarchical way, where we could instead choose to work on areas that are immediately applicable. And in this talk, I will try to touch on both, just to give some examples of how we've done that and how we're thinking about that. And it's possible to make sort of positive impact and to make progress in both types of ways. Obviously, if you're working on more directly applicable things, your impact is immediate because you're trying to build the thing that's facilitating the positive change. If you're working on more fundamental problems, you're not necessarily going to see the immediate positive impact, and oftentimes these technologies could be used either way, I guess in principle, right? So one of the areas where we've done as a group, I guess, lots of work in the last couple of years has been AI for mathematics, and it's hard to be more fundamental than this in terms of scientific discovery, given that mathematics underpins most of the other sciences and understanding of the world. And it turns out that there are lots of opportunities for machine learning to make advances there. So I'd say if you're looking for a more fundamental flavor of doing something that's still applied from the kind of vantage point of AI, mathematics does offer this. Now, this is not going to give this warm, fuzzy feeling of having help with something immediately, but mathematics and physics and these types of more fundamental sciences, they do play a very important role in how we understand the world. So one of the initial papers, and I'm looking at Peter a little bit here since he was involved, that we've done in that space, has been around maybe a more humble application of machine learning. And I'm saying humble in a sense that it's very much a human-in-the-loop kind of process, which I will describe in a moment. And speaking of ways of engagement, we've engaged quite deeply with domain experts in this space, with mathematicians from a couple of different fields. And they also played a very important role in this hybrid system. So rather than trying to automate everything away with machine learning and try to solve some big problem at once, what we try to do instead is use machine learning modeling to generate plausible hypotheses that can then be explored by human domain experts. The way this would work is there would obviously be some data, not to necessarily go into the details there. I mean, there will be some to follow anyway. Fit some models to that, apply some saliency to identify relations that our function sort of learning has uncovered, and then use that to generate hypotheses, test them manually, test them obviously through the hands and brains of mathematicians involved, and then refine the modeling and repeat the loop until something is finally proven. And we had some results here, actually in more than one subfield of maths, but topology/non-theory is the branch of the paper that I was involved with. And I mean, for those of you who don't know, knots are embeddings of circles in a 3D Euclidean space, and it's a particular branch of topology that looks into that. So we looked at knots, and we looked at some of their representations through these features, sets of features that correspond to knot invariants that are used to describe various properties of knots. And it turns out there are different types of invariants, and they were not really linked together, like the relationships between them weren't clear beforehand. So what we try to do is map between some of the algebraic invariants of knots and some of the more hyperbolic geometric invariants of knots at the time, and based on those mappings come up with some conjectures. So the data was something like this. Some of those invariants were scalar values, some of those invariants were polynomials, so then it would be like a list of polynomial coefficients and so on. And we fit machine learning, MLP, right? So nothing fancy. Looked at feature saliency for predicting the outcome, and it turns out that the model was predicting the selected variable, in this case the signature of knots, which is one of the algebraic invariants, and we could identify the features from the table that participated in that. Do a little bit of visualization, a little bit of exploration, come up with a new quantity. I mean, I'm saying we, obviously this was done by people who are actually mathematicians, come up with a quantity that fits that well, which was named natural slope, depending on, the geometry of these manifolds that knots can be in the knot complement. And finally, I mean, this has led to first an incorrect hypothesis that was disproven, and then later on to a correct hypothesis, which again, the details are not relevant. All of this is contained in the relevant papers, what these quantities are. But the point is, it was a novel mathematical relationship that was not known before, and it was identified ultimately through a collaboration between a team of people doing machine learning and between a team of mathematicians. And in this sort of framework of thinking about impact, knot theory has its applications in molecular knotting, in studying knotting in DNA, some applications through the Jones polynomial in statistical mechanics and QFT, some structures in the sun and so on. So it does have applications, but they're not direct. And if you look at the result that we've identified, its consequences aren't super clear. It advances some of the knowledge in knot theory, and there has been some work following that, but it's not super clear exactly what the practical impact was. So that's the consequence of working in more fundamental domains like mathematics, I guess, as an illustrative example. This is just to say that there has been a lot of work since at Google DeepMind when it comes to FR maths, and if you're not familiar with some of these that have taken this, I guess, far further, I would encourage you to read up because it's a really exciting area. One topic that's been close to my heart, and it was the first topic I worked on when I joined DeepMind 9 years ago, was medical AI. I was one of the founding members of that DeepMind Health research team at the time, and we were quite big at some point. Obviously, later on we had reprioritizations and everything, but at one point the DeepMind Health team was maybe over 100 people, maybe with a machine learning research team of between 10 to 20, and the rest being a mix of clinical experts, which we had in-house, software engineers, experts in other fields as well. So the first things we've done back then, and these are maybe somewhat historical papers from that point of view, so this is not necessarily modern, if you will, were that we looked at macular degeneration that we were modeling from 3D eye scans, from optical coherence tomography, and we've done modeling in electronic health records where we've developed sequence-to-sequence models that can identify patterns of patient deterioration early and signal alerts to clinicians that they can react upon. Now, Peter was alluding to certain types of papers, and obviously these qualify, but the reason why they qualify in that sense is that in their respective use cases, they were the very first papers that have demonstrated this with deep learning, yes, but at a clinically applicable level of performance. So how we approached this was working with clinicians directly, constantly reviewing things, refining our definitions, improving our data and ground truth and so on, and being very careful about metrics and operating points. But B, we would not stop until we reach a performance where, as tentative as that is, because it's a model trained on retrospective data, we could visualize this being deployed at a hospital tomorrow, hypothetically. Obviously, with the caveat that one does need to do all sorts of prospective studies, randomized clinical trials, and many other steps to ensure the models are robust enough. But we were already confident that the models we had were promising enough that they would make candidates for that. Which was obviously quite prominent at the time, and some of these models have since been re-implemented and are being trialed in different places. I'll just quickly go through some of the work, again, more like as an illustrative example that we've done on acute kidney injury, which we first, together with clinicians, identified as a potential unaddressed target, and then went on to address through the models that we built. It turns out it's a very prominent condition, even though it was one at a time for which there were no predictive or management solutions, really, at least from a more technological point of view. It affects very many people, leads to deaths and disability, people losing kidneys, needing to be put on dialysis, and serious health consequences with obviously high associated costs, but the human cost is what matters there. And there was no known method at the time that would identify people at risk that worked remotely good enough. So what existed was this criterion called KDIGO, which basically switches on as a criterion, not even when the injury occurs, but with a delay. So some amount of time after the injury has already occurred, which rendered it, I'm not going to say useless, but somewhat useless in the sense that it would only get flagged for clinical review for patients that were at the hospital that were already suffering from the condition and suffering from the condition for a while. The reason for that is that it was based off of serum creatinine levels, which takes some time to accumulate in the blood if the kidneys aren't working properly. So that was the motivation for why we went on and tried to build models. Speaking of understanding deployment pathways, there is another branch which isn't even shown here because there was a non-machine learning based piece of software that the rest of the company was looking into at the time. But we were really motivated by trying to reduce this delay between people experiencing the initial symptoms and condition triggering and clinicians being able to react and deliver care. And there are certain, not only known ways of delivering care that could be done earlier, but also because this management was always done significantly after the initial injury occurs, moving the needle and making this more preventative would enable for actually trialing of new drugs and new treatment pathways that can only work if the damage isn't severe yet. I'm not sure if it's very clear, but the point is that this is a very long curvy line, and there are many hours or days of delay. So we had this large data set with lots of things. The details are, again, maybe irrelevant for this purpose of this talk. It was extremely high dimensional in terms of the number of features we had. So identifying the sub-features here that actually were relevant and cleaning everything up was quite a task. This is sort of what I mentioned already. So we went on to build this sequence-to-sequence model, which would consume this data in some discrete set of daily buckets, let's say, as it's being aggregated and sent by the system, and would then pass it on to a recurrent neural network, which, again, like the feature representation was done in a certain way. I will skip the technical details to leave more time for the rest of the talk. And this deep recurrent neural network with some sort of a multitask setup and various bells and whistles we've added worked quite well. So we reached a level of performance that we were happy with, and here you can see various operating points as well as a comparison with some baselines at the time. Humans were interestingly also not capable of doing this, so this was already a system that was able to do something that human clinicians weren't themselves able to do. And we had a fairly good recall at the operating point with a number of false positives that we thought were plausible. We also really reviewed the false positives we had. Many of them turned out to be actually good predictions, just incorrect ground truth, because ground truth was sort of messy. And this is something, what this would look like, where there is a sort of a risk that's being predicted by the model. And when the risk exceeds the threshold, you will fire off an alert. An alert would be sent to clinicians. They would hopefully react, if the system were to be deployed in practice. And along with these risks and predictions, we also had future predictions of a number of different biomarkers that would then be able to give a little bit of color to why the model thinks that this is going to go down that way. And yeah, this was super exciting, I guess, but I'll skip through some of the technical detail again. The field has moved since. So these models are now, I guess, 7 or 8 years old, something like that. And what we are also seeing is that with the advances in foundation models and big LLMs, VLMs, and so on, this is opening new, unique opportunities within medical AI. So while like the project or projects that I just mentioned serve as maybe one pointer as to how one can engage in that space, the particular opportunity right now is to think maybe a little bit less, not to think about it at all, but think a little bit less about individual narrow use cases and think a little bit more about what we really want to build. And what we really want to build is systems that are capable of integrating very diverse multimodal signals from all sorts of measurements that are used as diagnostic tools and health indicators or predictions of various individualized models, and integrate that into a kind of a comprehensive health predictor or management tool. So we had some movements in that space recently. There was a paper we had, I guess, earlier in the year, not so long ago, that was reviewing actually some of the Gemini family models that were specifically tuned in a particular way in the space. The exact comparisons here maybe not so relevant, but what is maybe worth thinking about is a timeline, right? So this is what is plotted on the y-axis here is a score on one particular benchmark. Now there are various benchmarks, and this is a particular medical question answering benchmark that has its strengths, has its problems, like any benchmark does. But only 2 years ago, the best models that were trained for it weren't doing very well, right? And here we are 2 years later, already saturating the benchmark, basically reaching close to the level of performance that would enter into the zone of ambiguity in terms of answers that even humans aren't maybe 100% certain about. And all of this progress happened on a scale of 2 years. So if we extrapolate from there and think about, okay, where are these models going to be 2 years from now, it really gives us a frame to assess just the width and the depth of the opportunity we have. Because building on top of these types of models, I guess we should be able to achieve very many exciting things. And this is to say that LLMs have all of these problems we've all been reading about. This is a system that, again, integrates some amount of bells and whistles. It was an effort by lots of people so as to mitigate hallucinations, incorporate some levels of advanced reasoning, and obviously utilize the long context that Gemini models have. Similarly, there is even a system that was developed also, I guess, at Google recently which is more of a conversational diagnostic system that operates in a way similar to a primary care practitioner. So it's conducting a dialogue, a diagnostic dialogue with simulated patients, I guess, in this case, because obviously these are pieces of tech that one can't just deploy and try out in practice, but trained patient actors that took a pack of scenarios of these like vignettes with synthetic patient backgrounds and symptoms and so on, and were acting as real patients, both in their interactions with the system as well as in their interactions with other trained clinicians. And the surprising point here, and it's a very big paper in terms of everything that it covers, so I'm not going to go into any of the details, is that on most axes of performance, and there are very many axes that were considered, around 30, the system outperforms or matches the performance of human experts. So we already have early signs that technology of this sort can act in the same or very similar way to trained human professionals, which again has tremendous potential for increasing access to care around the world, especially in parts where it's not normally available. So yeah, another maybe natural point to stop. Yeah, go.
So you mentioned that sometimes we don't fully trust the ground truth.
Yes.
Because professionals can be wrong about the diagnostics. And I was wondering if that means that there is a limit to how well we can train these models to actually perform well in these tasks. And if so, do you think that there's a solution for that?
I mean, I guess the short answer is that. Oh yeah, for everyone. Yeah, sure. So I guess the question was, in case when the ground truth is uncertain and human experts aren't clear on what the ground truth should be, does that impose certain limits of what the models can do and what we can do with them? The answer is obviously yes. To an extent, I should just say that there are different types of uncertainty. In general, as we all know with machine learning when we train the models. And when it comes to the ground truth, there is a difference between something just being intrinsically uncertain and unknowable based on the presentation, and also subjective disagreements. One thing that is commonly done in this kind of space is that examples are graded by multiple experts, and then you can try to either model the distribution of experts' replies and mimic the human uncertainty, if you will, or you can try to really predict the consensus and to reach consensus. Because even with the grading, you could either have independent gradings of an example, or you can bring people in and have them discuss an example and then try to improve the quality of the ground truth. But yeah, normally you need a couple of human experts to facilitate that. I think there was a question there, yeah? Okay, so the question was if there is a notion of causality and causal reasoning within the model, or if it's a not regressive model. I mean, it is an LLM, so in terms of how the objective is trained, obviously it is not a regressive model. When it comes to planning and reasoning and that whole sphere of research, because it's a very wide sphere of research with LLMs, I guess lots of people are looking into this at the moment. So there is no clear-cut answer. I mean, you have lots of people being highly skeptical that models of this sort can do what you just said. But then there were some pieces of research actually indicating that you can do even like causal discovery in a sense with large language models if it's posed in a certain way. So while it's true that there are some maybe intrinsic limitations, things like in-context learning or how the model is instruction tuned and what it's trying to do, like based on the examples, especially because some of these systems also involve retrieval augmented generations where they consult external sources that have more solid ground truth, can mimic some of the reasoning that you're talking about, right? So it's not exactly causal in a very strict sense, but then almost none of the machine learning we've done historically has been causal in a sense in which the causal machine learning community would want it to be, yet the positive impact was there, and oftentimes it would be well aligned with what one would want and expect. Yeah.
As most AI medicine research papers are focusing on listening to data sets, and we're doing very well at these things. What are your thoughts on the next generation of benchmarks for medicine should look like?
Yeah, so the question was what future medical benchmarks should look like to capture some of the richness and the capability that's being developed. It's true that, well, at least as these recent papers show, some of the Medicare or USMLE are being saturated or close to saturated. So I guess in general for benchmarks and large language models or foundation models, there is this kind of a race where benchmark is only as good as it allows us to track progress, and these models are just advancing very rapidly. So I guess the short answer is that across the wide spectrum of LLM applications, not just in medicine, lots of people are currently working on evaluations and benchmarks, and it's one of the prime areas to be working in because we need stronger benchmarks to evaluate things more properly. When it comes to medicine in particular, it goes back to use cases, whether a model is good or not. While this gives some signal, obviously it does give signal, it really depends on the use case and the application. So if you have a particular way of using the model in mind, you can evaluate that use case directly rather than relying on other benchmarks to give you the signal for that. And some of the evaluation, for example, that was done here, as I mentioned, involved reviewing model dialogues, right, both through kind of AI critics, but also from the perspective of patients interacting with the system or diagnosis later on being reviewed by specialists and so on. So it's a particular use case, and then you can develop a framework of what works well, what doesn't in that use case, and just evaluate that narrowly. And I think that maybe then addresses some of the question, because it's very hard to comprehensively evaluate all possible future use cases of a system. There are just too many. Medicine is huge as a field. So even if there are more benchmarks, and I think here there were maybe, if I remember correctly, 14 that were used, so it's not just one. One still needs to go beyond.
So you think you will still have a specialized model in medicine, not one big foundational model that kind of works for most modalities in medicine?
So the question was whether there will be a specialist or a generalist model. I guess my answer isn't in relation to that. You could still have one model, but whether that, I mean, you don't have to. You can also have specialized models. But even if you have this one model, you would still want to evaluate it kind of one use case at a time and to confirm that, rather than to rely on a signal from a different benchmark to inform whether you do something here, right? So if you want to deploy, and this is not a deployment, right? These are just research papers that are highlighting the opportunity. But if at some point you reach a point where you want to deploy a system or really evaluate a system for deployment, you should evaluate it for the specific use case in which you're thinking of deploying, rather than using any of these benchmarks as, you know, this is just giving you signal, does this model look like it's trained well or not? But it's a very sensitive area, so one has to really evaluate deeply. Anything more at this point? Yeah, some questions there.
I have a practical question. Could you expand on how exactly this will make access to medical care fair? Because I imagine, for one, you need the technology to actually have this, and then if you get your diagnosis via this technology, you still need the medical infrastructure to actually get treated, and you also need the financial opportunity to get treatment. So I'm wondering, do you think it's actually realistic that in places that are very, that do not have a good social infrastructure, that it actually helps? Or is this just first world, it's going to be nicer when you live in the countryside?
So the question is, like, obviously on the difficulties of using technologies like these to make access to healthcare fair because of the underlying medical infrastructure that is obviously still needed. I mean, these papers, again, they are just a proof of concept, right, if you will. So it's showcasing that the technology can do things like this. They're not products. And you're touching on, obviously, one of the points I made earlier in the talk, that technology is not in and of itself the full solution. So you are completely right that even if one were to have a model of this sort and have it evaluated really thoroughly so that one feels safe deploying it, right, in principle, there is still the question of how this integrates with the rest of the health system that can then, synergetically offer something if the system is used in the process of delivering care. Because yes, in principle, if you look at systems like these, you can think about interacting with them or having them give you some signal, but at the end of the day, it's just software, right? You still need the rest of the healthcare system to make something real happen. And it's a very complicated question. So obviously, this hasn't been done yet. And I guess we'll just have to wait and see in the coming years if that promise gets fulfilled. But this is exactly why we need to be engaging, all of us as a community, right, with the people, the rest of the society, to make this promise of AI become reality, whether it's in medicine, obviously this is just one example, or whether it's in any other field. Sorry.
So apart from model making good predictions, what are some other important steps to take in order to make a model that is trustworthy and that experts will actually want to use the data they work? And what role does model explainability play?
Some of this will be addressed in section 3, so we'll let that speak. Not explainability, I don't have this here, maybe just a short comment here that Eric Topol, for example, who is one of the leading voices in medical AI, he's actually been pushing back on explainability a little bit, so I'll just highlight that briefly. And the reason is that explainability is oftentimes a bit approximate. So how people tend to see it is that, oh, if we explain a model and it looks fine, then this gives us confidence. But what you really want to do instead, ideally, this is not to say you shouldn't do explainability, is evaluate it robustly in the exact way in which you want, because explainability is not a replacement for that. And if you evaluate it robustly enough, then maybe you don't need as much explainability. So just in terms of that trade-off. But yeah, the other points we'll touch on. I think you had a question, right?
I wanted to ask about, you said that we should talk to other experts in the fields more. And my observation in this part, now that I was working interdisciplinary teams, and I wonder what you think, and also should we just have more interdisciplinary teams, or should we reach out to experts more? What is your opinion on that?
I mean, how these collaborations come about, obviously there are many ways of doing it. We obviously need organizational structures to make this work. Some of these opportunities also rest on our shoulders, so just talking to people more, engaging with them more. When it comes to medical AI, there are nice conferences like EEML'24, where people do come together from different, from medicine and from machine learning. I guess some such workshops exist for many of the other application areas at major conferences. I guess you would normally see it at workshops at ICML and Europe and so on. But meeting someone isn't the same as having a long-term established collaboration, right? So one way in which we've been going about it is either to, depending on whether we hire people or whether we contract with external sort of domain experts, but really to have some kind of a longer-term agreement in place for the collaboration as an institution. In academia, these may take a slightly different shape. Collaborations, which is through these frameworks for projects that exist for funding and so on. But I would say if you're planning on starting a project in this space where you would benefit from an expertise of a set of domain experts, don't start it without them and just counting on the fact that there is an open data set or an open benchmark out there, because it's immensely beneficial to have this kind of input early. Okay, so maybe with time in mind, because I just took a sneak peek at the time as well, I will move on into this section of the talk. I will speed through it a little bit, which is irresponsible, especially when it comes to responsible innovation, just to leave a little bit of time for wrapping things up in the end. But it is sort of the point where one way of doing good with AI is not doing bad with AI, and maybe this is a low bar to set. But it's also worth pointing out that something that doesn't come about as naturally, like if we're working in maybe AI for mathematics, it does come about in healthcare, as we'll see, is this notion that because AI tends to be trained on a lot of human data and this data comes from somewhere, it comes from systems that have not really been implemented ideally for various definitions of non-ideally that impact different people in different ways, so not fairly. We have a responsibility of building models that go beyond that and make better predictions rather than just reiterating what was done before. So this is a big field, and this is not the focal point of the talk, but I will just touch on some things maybe we've done or some challenges here, and I do believe that later on during the summer school there are some more talks about fairness, so hopefully they can cover more. Just maybe, like again in 30 seconds, for those that may not have looked into this before, but we want to have models that are fair, but it's actually kind of hard even if you want to do it, because when it comes to machine learning fairness, there are lots of metrics and definitions. They have been shown mathematically not to be satisfiable simultaneously. So it's not just about enumerating them all and hill climbing on all of them. Some of them clash in a way. There is a problem with intersectionality because we want for things to be intersectionally fair, but then you get a combinatorial explosion when you have a certain number of attributes you're looking at. Sometimes we don't have the data in the first place. Researchers just tend to apply their own normative viewpoints, and oftentimes satisfying more fairness in the chosen metric of the many involves some accuracy or performance trade-offs, which are sometimes unacceptable depending on what the predictive outcomes are. So we want fair AI, but it's not actually very easy to get there. So one thing we should be thinking about is that this mental model of let's first do the proof of concept, build a model, and then we'll somehow figure out how to make it fair tends not to work very well in practice because the step of just making it fair can sometimes be close to insurmountable. So there is this paper we've done recently which should have been online by now, isn't because it's stuck in the archive pipeline. This tends to happen more and more often recently, but you will get to see it and read it hopefully in a couple of days. What we've done is we've reviewed the published machine learning fairness papers, basically, from the top venues, top conferences that tend to deal with this for those who follow. And we've applied a certain framework for how we were reviewing them. We read through very many papers, which was very informative, obviously, and have then tried to see how machine learning researchers have chosen to address the topic of fairness in practice versus theory. Because even at these venues, you have some more theoretical papers where people from, let's say, the social science background or some other background come, and they will give this beautiful theory for how something should be approached, and then you have applied actual technical machine learning fairness studies, and you can see how many of those actually do any of the theoretically highlighted things. And that has been quite a fascinating experience. It's something we've suspected for a while, but here we've looked into this more formally. I will not go, especially considering time, into everything we've looked at. It's not maybe relevant. But I think the map will also speak for itself. So this is obviously scaled according to proportion. So both in terms of where do the people engaging with these topics come from, which is on the left-hand side, as well as, maybe more importantly for the models themselves, where does the data come from, which tells you something about what is being modeled and how. Again, it speaks for itself. It doesn't require much interpretation. Global South it has a kind of a fractal dimension here. It's not even, maybe probably two-dimensional on the plot. And that's not where we want to be. So that's something that definitely needs to be rectified, which means that a lot of the field that's currently looking into addressing these problems, they aren't really addressing them inclusively. And this speaks a little bit to, I guess, also the motivation for this summer school, as much as this is the Eastern European machine learning summer school, which is about representation and inclusion, that there is a reason why we organize events like these to raise awareness locally in various parts of the world, because this is not an acceptable situation. But the only way of resolving this situation isn't really to force people from the big blob to do all of the other, well, not blobs, but missing areas of the map. But it's for everyone to participate and everyone to help. Thanks with some of these. There are consequences to the under or over-representation in terms of the types of attributes being looked at, mostly gender and race. There are, more importantly, more of a there is a political dimension to how these things tend to be done, and a normative one as well, where race being a very rich sort of attribute, and I'm by no means a theorist, but what tends to be done in practical papers is black and white in a very literal sense. Nothing else exists. And you don't have to be a social scientist to know that this is not how one should be approaching this. Similarly to other attributes, very few tend to be looked at all. And there is a gap between what we want and what is currently being done. And these are the top venues in the field, and if it's not being done there, it's likely not being done in most other places. We've looked at some of these gaps, so we've looked at a slightly richer theorization of how one can approach measuring things in terms of, let's say, the ethnic background, which is in practice oftentimes as relevant as maybe race worldwide. And I think a lot of people from these areas will know about the history of conflict, etc. So I don't need to intro how big that can be and how bad that can be. But it's just worth pointing out that all of these more nuanced dimensions tend to be understudied. And we can see that going back to COVID-19 as an example, like there has been a lot of xenophobic hate and so on that, again, doesn't tend to be captured by the frameworks we just looked at. Because I did get a warning from Peter, I will gracefully skip through some more of the examples. Similarly, I won't go into the details here, even though I have some of the technical details on the slides, and people can obviously read through the paper later on, like if you're interested. But there is another interesting concept, which is that oftentimes when we think about fairness, we think about equal impact on groups, whatever the groups are. In healthcare, things tend to be slightly more complicated because of the fact that some of the sensitive attributes, I mean, age is maybe one very clear example, can be causally linked with the effects we're modeling. So this naive approach of trying to equalize everything uniformly is not the, theoretically speaking, right thing to do. It's not actually fair, whatever actually fair means. So we need to think methodologically in a very different way as to how we facilitate fairness in healthcare. And here we pitch one such method that's capable of addressing that in a very specific, let's say, class of models, and this was prompted by the findings that other groups have had in chest X-ray, computer vision diagnostic models, where researchers were able to, let's say, reconstruct race from the features of the models, and have found that to be kind of worrying because of the dimensions of discrimination that exist. Yet what we've shown in the paper is actually that when it comes to sensitive attributes, even those that you don't anticipate being encoded, actually the degree of them being encoded in the model has very little or rather nothing to do with whether the model is fair or not in this particular more causal sense. And that one just, again, has to look at some other things, but I will skip through this paper and the details, just because I want to get to the last section of the talk. Similarly here, as much as I apologize for skipping through things, but this is to say that when it comes to foundational models that I've been talking about just before, and the more general applicability opportunities that are arising, there was a question here about benchmarks and whether they're sufficient, etc. Indeed, they may, not be at the moment. So I would say that red teaming and red teaming done in a very comprehensive way with lots of groups and experts and participatory methods tends to be one good framework for approaching this, where we need to simply generate more and more data set and look at things in a more detailed way. And here in this paper, we actually combined this outreach to a number of different groups and health equity experts and so on, with even automated red teaming pipelines where the models would, well, it's not like the models would red team themselves, but we would build automated pipelines that would extend the coverage of that and make it all work better. But I'll take a very short break here and then try to rapidly, I guess, wrap up in the final part of the talk. So for these here, they simply did not exist before. So they were just created. Therefore, by definition, they did not exist before. But I mean, in principle, you are right for let's say, common benchmarks, right, that have been online for a long time, which is not to say that people have trained on them, have been meaning to train on them, but sometimes some of those questions may get discussed on other forums by people, so they may leak in various unanticipated places. You do have tools, or other companies have tools internally where they can verify like the closest data points to something and try to identify if something existed before or not. They're not perfect, but it's something we do look at when we do things. It is a risk, though. You do have a point. Okay. Maybe finally, and we had this actually very comprehensive report going through various aspects of these more advanced systems. This is to say, going to hear that rather than hoping to do good by the virtue of attacking some problems, there is another way of thinking, which is, can we put human well-being and positive impact as a direct objective and try to optimize towards it? And it's something we should increasingly be thinking about, not maybe in every single application, but there are a number of applications where this will make sense, especially for the future where we will have more and more general models that oftentimes we use maybe even as personal assistants. So if you envision a future like that, where you have your assistant that's giving you some recommendations, are these recommendations meant really to, one would think, right, to do you good? And if so, how can one design these assistants so that you as a user get the most direct good out of them? And there are various, aspects these systems may have. They may execute tasks for us. They may simply give us advice. They may influence our behavioral patterns through repeated interactions. And as any sort of long-term repeated interaction, unsurprisingly, there are many aspects of that are worth studying. And I think as a field, we're just scratching the surface of this because these types of systems simply did not exist before in the form in which they can exist right now. So if we want to build assistants that will primarily be used to optimize human flourishing and human well-being, how do we go about it? So I started the talk by talking about good, or rather asking about what it meant for something to be good. When it comes to optimizing for well-being in particular, we can ask a similar question, and it's an equally philosophical one, so maybe not worth dwelling on as much right now, given the time remaining. But it's worth saying that similarly to common good, personal individual well-being is another very commonsensical thing that I think we all have a mental model of, that again, very many people very strongly disagree upon. So there are views of well-being which say that it's something very subjective, like you feel good or you don't, and in terms of soliciting that feedback from people, you can ask them, how are you feeling today, and you can get some answer on a scale, or there can be a number of scales and you pick and choose, right? That's one way of thinking about it. Another is that some people say that there are some objective values and objective measures of well-being that generalize across people that we should be trying to optimize for, and this gives us a very different framework. When it comes to both objective and subjective definitions, it's sort of culturally specific, where self-reported measures by people will vary depending on who they are, where they are, and their culture, how positive or negative they view things, how much value they put on different aspects of well-being, right? And the same problem comes to the objective definitions, which is if you're trying to make something, universal, who gets to decide what is universal? Does this exist? Is this the right way of going about it? So there are various, unsurprisingly, existing philosophical theories of well-being, whether it's a balance of pleasure and pain, whether it's fulfilling your preferences and desires, or, as I was saying, these objective list theories. Now, when it comes to preferences, we also have short-term desires, we have long-term desires. Sometimes we are not logically consistent as people. We may desire multiple things that are mutually exclusive or inconsistent in various ways. So even if we want to technically, let's say, map onto theory like that, we may face all sorts of technical and practical challenges. So if we want to build technology for well-being, it's not super clear to decide on the direction, which again speaks to the point of actually engaging with the community. And this will not kind of remove the ambiguity in and of itself, But it's not something we as technologists can just decide to do, right? Because we wouldn't know exactly what to do of all of these options. And yeah, I mean, again, I think I'm at time, so in order to leave the time for questions, I will just go through this quickly. But yeah, there are some drivers of well-being that people tend to talk about, which is having autonomy, relatedness, engaging with other people, like family bonds, friendship, and so on. There is personal fulfillment. There is obviously physical and mental health. And there is a hierarchy of needs, right? We could try to, first off, eliminate poverty in the world, right? And then try to do more. Or we could try to do everything simultaneously. And depending on how we choose to approach things, it may lead to different types of technological solutions and different research projects that aim to address different aspects of this. When it comes to technology itself, to date, not just looking forward, there have been conflicting findings. Some of the technology that the world has developed has had an adverse effect on, let's say, mental health. Some has, on the other hand, been identified as potentially helping with some of the mental health crisis that exists. Same goes for other areas of life, where on the one hand you have the kind of dystopian surveillance capitalism, right, scenario. On the other hand, you have AI being used to help improve well-being at work. And I guess AI systems and AI systems of the future live on this spectrum. So speaking of the dual use of technology and making an informed choice as to what we build, it's up to all of us individually and our organizations to choose the right path. So there is a great potential. There are many pitfalls. We can end up on either side of the spectrum. And yeah, we should be mindful of how we go about it. And we give some set of recommendations here. But with this in mind, maybe just final point, which is saying that obviously I was speaking about participation. There is the set of domain experts that we can work with, yes. There is also the more democratic view of the overall participation of society and potentially affected groups. And it's something, you know, we are doing at the moment and lots of people talk about, but it's actually not super simple because there are various ways and degrees in which participation can be facilitated. You could say that there was the plot I've shown in terms of, let's say, the origin, provenance of data sets, that having your data incorporated in some system, in a training of a system or in an evaluation benchmark of the system, is a form of participation because your problems are somehow being mapped or evaluated, but that's a very narrow form of participation. You could alternatively build a system, go to people and ask them for feedback, right? Is the system good or bad? But you've already built the system. You could ask people to contribute to the development of the system, but you've defined what the system is and what the objective is before you ask them to participate. Or you could go to these communities and have them decide and define what the system that is meant to be built is, what the objective is, what the metrics should be, and then you go and build it. Therefore, disempowering yourself in a way and empowering them. And depending on which of these options you choose, it leads to different outcomes in terms of what participation means. So there is this quote above which sort of refers to it obviously not being done in a very inclusive way usually, which is, I participate, you participate, he participates, we, etc., they profit, right? Which is kind of extractive and speaking to the extractive nature of a lot of participatory work being done to date. So it's a pitfall that I would just highlight is meant to be avoided. And with that in mind, and hopefully not being assassinated by Peter for running very close to the limit, I will put this at the end. But I mean, if there are any quick questions, and I will also be there at the break, feel free to ask. Thanks, Nenad. Okay, sure.